As our next example, let's look at a sphere. This is a solid sphere that has charge evenly distributed throughout this sphere. So we're going to draw a Gaussian shell inside. We're going to draw a sphere, concentric. And from the center out to our Gaussian shell, we're going to have little r. From the center out to the edge of the non-conducting sphere, we're going to call that r naught. So in the first case, we're looking at when r is less than r naught. Well, we need to know how much charge is enclosed inside this Gaussian shell. So let's look at a parameter density, charge density, that's rho, and that's going to be equal to the charge divided by the volume. And the volume of a sphere, you can look it up in the book, is 4/3 pi r cubed. To get Q enclosed, it's just going to be the ratio of the charge inside versus the charge outside the Gaussian shell. Well, the first thing we need to do is solve the this expression for Q. So let's solve this expression for Q. So the Q inside of any spherical solid sphere is equal to 4/3 pi r cubed times the density. And now Q enclosed is just going to be the ratio of what's inside the Gaussian shell divided by what is the charge inside of the hole in this case it's going to be r naught cubed because it's everything, rho e, and this is just a fraction, and then we have Q because we're wanting to know the part of Q is inside Q enclosed, this Gaussian shell. Well, the 4/3 goes away, pi goes away, rho goes away, the densities, and that just leaves me with Q enclosed is equal to r cubed over r naught cubed times the total charge in the sphere. Now let's do our integral. Since this is symmetric inside this sphere and the charges are distributed evenly, throughout this sphere. That means that the electric field has to be constant throughout all of this Gaussian shell. So I can take my electric field magnitude outside, and then I'm going to have the surface integral of the Gaussian shell is equal to, well, Q enclosed is equal to R cubed Q over R naught cubed epsilon naught. And the surface integral of a sphere, the Gaussian shell, is just equal to 4 pi r squared. And solving for E, we get r cubed Q over 4 pi epsilon naught r squared r naught cubed. And simplifying, we can take r squared out of the bottom, take r squared out of the top, and there's our answer. R times Q divided by the quantity 4 pi epsilon naught r naught cubed. Now, what are constants? Well, Q is given to me, so it's a constant. 4 pi is a constant. Epsilon naught's a constant. R naught is a constant based on the sphere. And the only thing I have here that would be variable is R, because I'm looking at the electric field as a function of the radius. So because of everything being a constant but R, basically R is just the first power. Anything to the first power gives me a linear function. So I'm going to have till I get to R naught, I'm going to have a linear function. And the value at this top point is going to be Q over 4 pi epsilon naught r naught squared. Because r is going to be equal to r naught, it's going to cancel out one of the r naughts in the bottom, and I have this straight line. And this is consistent with what we would think that value would be. Now, let's consider the outside. And I'm not going to go through all of the derivation, but let's think about this. All of the charge would be inside this spherical shell. And isn't this just the situation we saw previously, where the shell encloses some Q inside? And so for, let's see, where's a good place to write it here? I guess I'll write it on the next page. For R greater than R naught, the electric field is just going to be Q over 4 pi epsilon naught r. And so now this graph is going to be 1 over r, and it's just going to decay from that top maximum point, 1 over r. So here we see that because it's a non-conducting sphere and it's solid, there is an electric field inside of this material, and the electric field gets stronger until it reaches the surface, and then it decays or gets weaker as you go further and further away from the shell.